to go. So Peter, I'm gonna let you lead at this point. And who in the committee is there? Well, we can talk about it afterwards, is how to handle the discussion afterwards. So okay. All right, Peter, all yours.
All right, great. Thank you everyone for being here. So let's go through, let's see the slides over here. All right, so let's do a brief agenda. So we'll have 60 minutes of presentation here, starting off with about 5 minutes of context for friends and family. Then into the technical meet, we'll go through open questions and discussion, and then the thesis committee will deliberate. So we'll start right after the hour here. So, okay, so I'd like to start off with some comments that are adapted from some remarks that Mark made, actually. So if you look at the history of aircraft design optimization, right, in about 1956, we got the first jet airliner. Today, we've got something that looks pretty similar. But under the hood, a lot is actually different. In terms of the fuel economy, we've gone from about 45 passenger miles per gallon up to about 120 or so. If you look into the future, you can target numbers as high as 160 passenger miles per gallon. Now, it's kind of instructive to think about what are the technologies that actually got us to each of these levels. Now, if you look in the past, the mindset was something called satisficing, which is basically a decision-making heuristic that you go through when optimization is intractable. It's kind of the engineering equivalent of good enough, right? Today, there have been massive advances, especially in propulsion, but also in subsystem level optimization. So taking the problem, splitting it up into different disciplines and optimizing those together. Now, looking forward, most of the fuel efficiencies gains that we expect to see are actually from taking the whole system together. This is called multidisciplinary design optimization, or MDO. It's about finding the synergies between subsystems rather than within them. And the particular flavor of MDO that we're going to be focusing on today is what's called conceptual MDO. This is kind of the initial study of design trade-offs that you go through, basic feasibility and sizing. And the idea here is that we're modeling wide, not deep. So we're talking low, medium fidelity models, relatively simple, but maybe hundreds or even thousands of them. Typically, those are lumped into what we call disciplines, or different kind of ways that you can analyze the design. Aerodynamics, structures, propulsion, but there are many dozens of others that you could consider, and all of these interact with each other. So why do we care about this particular kind of early stage conceptual optimization? Well, the first reason we might is that most of the performance of the final design is actually determined by your early stage decisions. And a lot of this kind of low-hanging fruit, you can't capture those opportunities later if you miss it in the early stage. Similarly, you can't really fix the problems later if you don't catch it in the early stage. So that's really what we're after. Secondly, these days, there are a lot of new technologies, specifically thinking about electric aviation, drones, UAVs, that are enabling us to kind of go back to the drawing board and look at the early stages of aircraft design again. This is kind of exemplified here by a lot of the electric vertical takeoff and landing aircraft. And even after 10 years of playing with these technologies, it's still kind of the Wild West. There's not a lot of convergence in terms of what these necessarily look like. The final reason is that optimization itself, a lot of times we think about getting to the optimum design, whatever that may mean. That's really only about 10% of the value. A lot of the value of doing this exercise is actually in determining what questions you should be asking. What are the market trade-offs that you might look into? Where should you spend your R&D budget? What kind of model assumptions are you most sensitive to? So with this in mind, we can kind of look at, okay, we've done all this research in MDO, where do we kind of stand? This is recognized in a couple places, most notably in an MDO colloquium in 2010. The ultimate benchmark of a field's impact is how much it's actually getting into industry. And going through the literature, we see kind of a mixed bag. On one hand, everyone recognizes the immense power of advanced optimization methods to solve some of these previously intractable problems, and there have been headwinds made. At the same time, it's usually this double-edged sword where actually implementing these in an industrial setting has a monumental level of complexity in some cases. So because of this, the same colloquium concluded that the actual use of genuine MDO is somewhat limited. So that's kind of the context in which this thesis starts, which is basically how do we actually take some of these big research wins and translate them into more industry impact. And the contention here is that we basically need to do optimization while considering all costs. We use costs here deliberately because that's kind of the language of optimization. Typically, we're minimizing some kind of a cost function. If we think about what our typical mental model of optimization, okay, we've got a problem. It's got an objective function that we minimize. It's got design variables, the things we're changing, and then it's got the constraints. And that result has some cost associated with that. If we want to kind of think about it more, we could also think about the computational cost of getting to that solution. But there's a much broader picture here that we also want to consider. First of all, we actually need to go from our problem specification, which is usually, in a Word document or some kind of written form, verbal form, and translate that into a precise mathematical paradigm. And actually doing that, depending on the framework, can be very easy or it can be very difficult. Similarly, oftentimes we don't get that right on the first time. In fact, we almost never get that perfect on the first time. So there's a cost associated with going back to the drawing board and kind of reformulating that problem. Maybe we want to freeze something and optimize over other things, or maybe we want to study what happens if we change the sensitivity of certain parameters. Secondly, in addition to the problem-specific stuff, there's also physics modeling that we need to incorporate. These are, not specific to the particular airplane you're designing, but just basic modeling like aerodynamics, structures, propulsion, different pieces. Getting those into the framework has a modeling cost. Ideally, the design also doesn't end at the point design phase here. Ideally, you can carry this forward. And if you're going to build this, often there's some kind of a design review process you go through. There's an interpretability cost of determining, can you actually convince an external audience that this design, the way you got to it, is trustworthy? How interpretable is this optimization process? And again, that's something that we can kind of consider when we sketch out a framework. Finally, even after the final design is made, after you're building it, you may get halfway through the design, find that one of the components isn't performing up to spec, and now you need to kind of redesign around that, right? Or you want to track a digital thread or a digital twin as you have some kind of ongoing hardware. And again, a framework can potentially support you through these steps of the design process. So the takeaway here is that modern scientific computing capabilities enable unprecedented problem scale, but they really push the human limits in terms of complexity management. And that's really what the thesis is aiming to tackle here. Now, if we look at kind of, okay, what do people do today? Because optimization is used in some forms in aircraft design today. There are three main paradigms that are out there. The first one is called black box optimization. This maps very closely onto our mental model of optimization. You get your analysis tool, you wrap that inside an optimizer, and then you iterate. And this encompasses probably 95% of industry codes today, or some flavor of this. The reason for that is that they're very easy to implement. Right, so you can go from your whiteboard drawing to code very quickly, and they basically let you model more or less anything. The downside of this is that the runtime of this is not very scalable. Once you get beyond, say, a dozen design variables, it starts to become exponentially slower to run. So because of that, this has motivated some research into other possible paradigms. The first one that has gained traction is gradient-based methods with analytic gradients. So this is similar to black box optimization, but you provide exact derivatives for every component model that you stitch together in order to accelerate the optimization process. And that gets arguably the best speed and scalability that you can achieve here, but actually implementing those derivatives, especially for custom models, becomes somewhat expensive on the user development side. The third kind of approach which is done is what's called disciplined optimization. And an example of this for the aircraft design crowd might be GPKit. The idea here is that basically you take the mathematical space that the user is allowed to model in and you restrict it either to convex functions, geometric programs, some flavor of that. By doing that, you can make certain assumptions about what the user's code is like. Because of that, you can make it easy for them to model their code, but also pretty fast to run, right? The downside is that by restricting the user to this mathematical subspace, they may not be able to model all of the physics that they wish to model. So the core scientific question of our thesis is basically, is there a way that you can do okay, at least, in all three practical metrics simultaneously? And the contention is that code transformations, which we'll define in the next slide here, are a path to doing that. And that's sort of what this thesis is about. So to kind of overview the specific PhD contributions, the first one is this code transformations paradigm. We'll define it, we'll give a proof of concept along with some case studies. Secondly, we'll fill that out with some traceable physics models that go inside that. Third and fourth, we'll talk about possible strategies to incorporate black box code into this framework. And then fifth in the thesis, there's a system identification study, which is another case study using this framework, but we'll skip it in this talk for time. Let's see. Okay, so let's start about what is a code transformation? Well, code transformations at a high level are basically any kind of transformation you can apply to code that intercepts their code, analyzes it, applies some improvement, and solves an augmented optimization problem instead. That's a pretty broad definition right there. And that actually encompasses a lot of modern techniques in math and computer science, most notably automatic differentiation, but also sparsity detection, automatic scaling of problems, log transformation, eliminating common sub-expressions if you can find redundant computations, computing on different backends, things like that. And what's the point of making this abstraction? These are all, fine by themselves. The reason we pull it out here is that it recognizes that all of these techniques are enabled by the same underlying requirement of code, which we call code traceability. This is essentially the ability to form and manipulate a computational graph of your code. We'll show what that means on the next slide here. The basic reason for this, though, is that it means that if we can solve this traceability problem, if we can make it easy for industry engineers to write traceable code, we kind of get most of these transformations for free. And it means that the user can get fast code without necessarily implementing all of these techniques on their own, without necessarily being applied math or computer science experts, only being experts in their engineering discipline. So the first contribution of the thesis here includes a proving ground for evaluating what these frameworks look like. That's called AeroSandbox. It's a Python package. It's open source. It's available on GitHub. And it's a proof of concept of what these code transformations could look like in design practice, both for airplanes, but also for other engineering systems. We'll start by talking about some of the numerics and the optimization that's happening inside this. Yes. So first, okay, so we talked about a computational graph earlier as being the key thing for, whether a code is traceable or not. What do we mean by that? Well, a computational graph is essentially a way to map out the execution tree of a piece of code. So imagine you have some expression here, right? You can map out what sequence of operations you have to perform on that step by step in order to get to the result there, right? And this is a directed acyclic graph here that you can make for most computer programs, assuming that you can kind of see inside the black box of different functions. Now, in practice, these computational graphs can be absolutely massive, right? So this is actually a graph for one airfoil analysis at one aerodynamic operating point. And so what is AeroSandbox really? Well, it's actually a tool for manipulating and transforming these giant computational graphs under the hood. And while doing that, it makes certain choices that tend to work out well for engineering analysis code, as contrasted with something like machine learning. And we can talk about some of what those are if people are curious. So how does this actually work out in practice? Again, our three metrics, we want to go from an idea to code fast, we want to have speed and scalability, and we want mathematical flexibility. Well, if we compare to black box optimization methods, we can test on something like the Rosenbrock optimization problem. This is kind of a standard test case in optimization. And here we work with an n-dimensional variant that basically gives us a knob to change the difficulty of the problem. Now, as we change the difficulty of the problem, the number of design variables, how does the computational cost scale? We can evaluate for a bunch of different methods. So up in the kind of upper quadrant here, we've got gradient-free methods, Nelder-Mead, genetic algorithms. Then there's a line that corresponds to gradient-based methods, BFGS, SLSQP. And then finally here, we've got our method here. And the reason why you see fundamentally better scaling here on the blue line is because it automatically detects and exploits the sparsity that's inherent in this problem, right? But critically, it does that without the user explicitly giving any kind of sparsity pattern between any of the variables. So that's an example of how you can kind of get fundamentally better scaling automatically without any user intervention if you can get traceability here. So the next thing we can kind of compare against is disciplined optimization methods. Again, this is something like GPKit, and that's in fact the example that we use here. GPKit became very used for aircraft design optimization in the past 10 years, mostly because it observed that many aircraft design relationships fall into this kind of nice mathematical form that's amenable to this particular style of optimization. One of the test cases that's within the GPKit suite is a beam analysis problem. So essentially, we have a beam, we discretize it, we apply a distributed load to it, and we try to analyze that using an optimization framework. we can kind of compare how that alone performs to a framework that uses more transformations simultaneously. So here we've got, again, the problem size here, which is the number of beam discretization points, and the wall cost runtime here, or the wall clock runtime here, which kind of gives the computational cost. And you'll see that GPKit offers two different numerical backends, CVXOpt and MOSEC, one of which is about an order of magnitude better than the other. But you can still do better if you apply further transformations to that. Again, there's sparsity in this problem that you can take advantage of. What's particularly interesting, though, is that if you formulate this problem, straightforwardly, one of the ways that you can speed up here is that this is actually a linear problem. It can be solved in one shot with the sparse linear solve. That's what gets you the blue line here. However, if you use the same geometric programming formulation, so the same math, just a different solver, that gets you the red line. And so you can still get a speed up even on geometric programming compatible problems by using a solver that exploits more of that. And you get fundamentally better scaling here. The final kind of comparison we can make is how does this work compared to an analytical gradients method? So where you're actually providing gradients for the problem at hand. And here we do another beam design optimization problem, which is actually taken from the example suite of OpenMDAO, which is a framework that focuses on these methods. Here, it's similar to the previous beam optimization problem, except that we're varying the thickness of that beam along the span, and we're trying to minimize the tip. We're trying to minimize the tip deflection while constraining the amount of total material that happens. And what's interesting here is that there is a runtime benefit to using these methods, but what's particularly interesting is the number of lines of code or the engineering complexity associated with that. So here we compare what a code transformations implementation looks like versus an analytical gradient. And we find about an 8x reduction in the number of lines of code to formulate that. And because of that, again, that's an imperfect metric, but it corresponds to a decrease in the amount of engineering time. Often that means that you may be willing to pose questions that you might have otherwise deemed too complex before. And in fact, this code is short enough that we kind of show it here on one slide here for this beam design problem. So what's actually happening here? Well, we're defining constants here, right? Initializing an optimization environment. And then we get this very modeling language like syntax where really we're just implementing the actual governing equations themselves, boundary conditions, and then the actual solve is just a single line here, right? So it's pretty abstracted in the sense that the user doesn't have to tweak anything if they don't want to. There are sensible heuristics applied throughout to kind of get them good enough results. Now, under the hood, they can expose as much of this as kind of they wish, but at least the learning curve is made more shallow by having a simple default API here. So what are kind of the pros and cons of this code transformations framework? Well, the benefits is that you can get the performance of efficient code kind of without having to write efficient code. So you get comparable speed with not as much effort as it ordinarily might take. It also abstracts away the optimization specific details here, meaning that you can focus on asking the right engineering question rather than focus on getting the numerics perfect. The downside of this are twofold. First of all, we need to actually intercept the user's code in order to make that computational graph representation. So we have to make some assumptions about what that user's code does. In particular, it has to use our numerics library to achieve that. And so framework syntax becomes critical because as soon as you start asking the user to deviate from the workflow, you're potentially completely negating that kind of ease of use benefits. So you really have to think carefully about what is the user experience going to look like. Secondly, the user's code style also has to, you have to think about how you're going to work with that. Engineers like to write a type of code that's often called procedural code that looks like a script or a spreadsheet. That's kind of how they kind of build up analyses and then flip it around into an optimization framework. A lot of automatic differentiation frameworks, other code transformation frameworks expect what's called functional code or pure functions here. And that's not necessarily the best map onto how engineers naturally write code. We can talk more about that if people are curious. So how are we actually making these computational graphs? Like I said, we basically have to intercept the user's code. But the trick is that we want to be a little bit tricky about how we do that. We want to basically silently swap their math library in a way that they don't really notice. So what do? We basically take the standard kind of Python math import that a user might write code in, right? And we swap it out with our own version, which basically duplicates the API one for one, parameter for parameter, right? So we can intercept their calls, right? meaning that if they pass in a type or a type of an array that needs derivatives or needs sparsity, we can apply the appropriate framework to that. But if they don't do that, it's essentially a pass-through into the basic NumPy framework that they were expecting to use anyway. And the nice thing about that is that existing code that's out there, provided it's written A, in Python, and B, with common packages, NumPy, SciPy, things like that, can basically be ported over one for one with a couple caveats to that. And the goal here, again, is it's all about the learning curve, right? If an engineer knows Python, we want them to be able to more or less jump into this with minimal additional learning. So that's kind of the first contribution of the thesis here. The second one is, okay, we built this framework, but now we want to test out, okay, is this actually practical for engineers? And the second thing that we can do is build analyses on top of this optimization core to figure out, okay, if we stress test a diverse range of computational patterns, is it actually going to work in practice? And then if we want to actually pose aircraft design problems, does that work? So underneath the hood, there are a lot of models that have kind of been implemented on top of this, all your kind of bread and butter aircraft design models. Here, we're going to talk about just a couple of them, specifically the aerodynamics and the flight dynamics one, mostly because they have the most interesting visuals, I think. But happy to talk more about the areas that people have interest. So the first thing is that, okay, if you're going to do engineering analysis, a lot of engineering analysis requires discretization of some sort, otherwise known as meshing. And there are different ways that you can do this. So the first thing we do is we build a differentiable geometry stack, a differentiable meshing stack, which basically can take abstract geometry representations, kind of your AVL style aircraft model, and then form a 3D mesh out of that. And it can form a 3D mesh at different levels of what are known as degenerate geometry. This is taken from a strategy that's used by OpenVSP a lot, right? So you can have meshes of individual, spars. You can have it of thin surfaces, of full outer surfaces, different parts of the aircraft, depending on what analysis you're doing. The benefit of doing that is that if a user wants to add an analysis, the learning curve is a lot shallower. They don't have to do their own meshing, right? And secondly, if you have a multi-physics problem, so an aerostructural analysis problem, you don't have any kind of interpolation or projection error between different meshes. You can use the same meshes for different problems and solve it exactly that way. So that's kind of the benefit of making this abstraction. So what are some of the models that are implemented here? Well, the first one, again, bread and butter, is a vortex lattice method. This is used every day for rapid stability and control analyses of different aircraft, initial configuration, aerodynamics here. And it stress tests the robustness of the geometry stack, as well as basic linear algebra, kernel operations, things like that. The second thing that we can do is a lifting line-based aerodynamics analysis. That's similar to the vortex lattice method, but compared to it, it has profile drag, it has faster runtimes, and it has better optimization stability. There are a couple different lifting line models that are implemented. The first one is traditional. It's basically a linear lifting line model. So here, the CL alpha, the lift curve slope here, is assumed to be linear, and then you can do some simplifications based on that. There are also quasi-linear, fully nonlinear models. Those basically give you increasing fidelity in certain interesting aerodynamic cases here. And these stress test nonlinear systems of equations, as well as making a computational graph through value-dependent code execution. What I mean by that is if you have a nonlinear solver, you don't know a priori how many iterations that's going to take to converge, right? So the computational graph isn't fixed as soon as you run it, right? So in some sense, you have to embed in a variable computation step in there, which can actually dynamically adjust depending on how many iterations that may take to converge. And that's an interesting stress test case there. And just as an example, again, by having the uniform geometry stack, we can do interesting problems like an aerostructural analysis problem very quickly just by kind of stacking these different analyses on top of the same meshes. The final aerodynamic model that's included here is what's called aero buildup. And this is the one that we probably use the most often and is one of the more interesting ones in my opinion. This is basically a fully differentiable DATCOM-like method or a semi-empirical aerodynamic buildup. So in regions where flow is well behaved, it uses theory-based models. In regions where it's not, it uses extrapolations to wind tunnel data. And it's essentially a C1 continuous, so a smooth model of that across all ranges of kind of Reynolds numbers, Mach numbers, orientations out to, kind of the limits of where you can reasonably get with wind tunnel data. And this is stress testing, table lookups, heavy conditional logic based on all the different kind of as well as can you actually guarantee continuity when you're stitching across, anything from, very low Reynolds flight all the way to transonic, high alpha flight continuously. So just some kind of, interesting things about what that looks like. This is a graph that I find pretty cool. So a lot of people have seen the CL alpha curve, kind of your classic lift curve slope with alpha. But this is a graph that extrapolates that to 90 degrees angle of attack, plus minus 90 degrees angle of attack, and 90 degrees angle of side sled. And so it's kind of interesting to see what that graph looks like when you expand it out here. This is for the Firefly aircraft, which we'll show in a little bit. But you can see that, you get modeling here in the kind of linear regime, and then as you go through stall and then into deep stall, you get more and more interesting effects, but it's all C1 continuous through it. Similarly, you see kind of the same thing with the drag coefficient. And this is just a neat perspective that we don't often get to look at. Another thing that we can look at here, again, for the same airplane, which we'll show in a bit, is, all right, if you start from any orientation, any 360-degree orientation, what's the moment, the CN and the CM and the CN? So where's it going to point the nose, right? Is it actually stable or not from extreme orientations? In this Firefly vehicle, we were getting launched out of an airplane at 90 degrees angle of attack. And so we wanted to kind of check whether it would passively stabilize, and if so, how quickly. And so that's kind of the motivation for a diagram like this. You can quickly see, is it going to kind of weather vane back where it should or not? And then in the thesis, the written document, there are a couple of validation studies for these various aerodynamic analyses methods. We won't really go too much in depth here, but in short, the vortex lattice method is the most accurate one for stability and control for moment prediction, whereas the lifting line, the aero buildup ones are more accurate for performance prediction, CLCD and things like that. One of the other kind of models that we built on top of this framework is rigid body equations of motion. This is useful both if you want to do pure trajectory optimization problems, but also if you want to do combined vehicle and mission design problems together. It's variable fidelity, so you can switch off, at the simplest level, it's essentially just energy accounting of an airplane. At the fastest level, it's integrating moments and forces to actually time domain integrate that through some kind of trajectory. And you can switch off which modes you care about. This here, of course, it's testing stiff ODEs with many relevant timescales together. You may have a control surface which actuates at 5 Hertz, but have a phugoid mode that's, 1 per 100 seconds or something like that. So you can kind of think about those together, and there's some interesting optimization challenges with that. A cool case study here of what that looks like is an air racing trajectory optimization case study, which we demonstrate in the thesis here. This video isn't gonna play, bummer. And here, basically, we optimize the trajectory of a fighter jet through a low altitude canyon, flying as fast and as low as we can. And we actually discover some interesting real maneuvers here, such as an inverted roll here when you go over the top of a mountain, a ridge crossing maneuver here. This is kind of interesting here. This problem is actually, essentially a model predictive control problem over about a 5-minute decision horizon with sub-second decision resolution. So that's kind of going back to that idea of multiple different scales that interact here. And it's highly non-convex. Do you go to the left of the mountain or do you go to the right of the mountain? And there are kind of some interesting heuristics and challenges that you can do to make that a little bit better behaved. The final contribution, or the final analysis that we contribute, is a linearized aircraft stability analysis. And so an example of this would be if you're designing an airplane, right? You have your short period mode, your Dutch roll mode, and you want to place certain constraints on that, the damping ratio, the frequency associated with that. Can you actually do pole placement of those at the same time that you're designing the rest of the airplane? And now with a differentiable map through this eigenvalue decomposition, you can actually do that. And so that means that you can consider stability and control from the earliest stages of design. And especially when you get into kind of weird designs, often stability and control is the thing that kills a lot of otherwise promising designs. So it's useful to be able to kind of bring that in early. So when developing this framework, we went through what we call a spiral development process here. What we mean by that is that, about every 3 to 6 months, we iterate through this cycle of, okay, using this framework, let's actually build, design, build, and hopefully fly an airplane and see how we can improve that aircraft design. And then we flip it around and we do a retrospective, which is, okay, based on that airplane case study, what are the things that were easy, what was hard, what was easy to pick up for new users, and how can we actually modify the framework itself to kind of make that better? And so we've gone through this loop maybe 3 or 4 times with different aircraft, and here we'll talk about some of those aircraft, what they look like, and some of the things that we learned or capabilities that we added as a result of that process. So the first aircraft that we'll talk about is slides are so finicky. Okay. The first aircraft that we'll talk about is MIT Firefly, which some of the people in the room worked on, especially Julia here, who did some of our hardware construction. Firefly is basically a tube-launched micro UAV that launches out of a FA-18 at, again, 90 degrees angle of attack here. It's air deployed at Mach 0.8 at 30,000 feet. We want to maintain Mach 0.8 flight for 60 seconds. And the objective here is we want to maximize the total range. So this airplane, the tricky part with it is how small it is. It's about the size of a Pringles can or so, right? So we're really very volume constrained, and everything is fighting everything for volume requirements that it wants to use. So we set this up as a design optimization problem here with 6 coupled disciplines. So aerodynamics, structures, stability and control, propulsion, optimizing the trajectory, and then again, the big thing here was the volume, just making everything fit. And in total, that optimization problem is about 4,000 variables, about 8,000 constraints, a lot of which come from that trajectory formulation there. And it's nonlinear and non-convex. And the cool thing here is that, with code transformations, we can solve this pretty quickly in only a couple seconds. And that means that it's fast enough that we can do interactive design here. The other part that's equally interesting is that we can solve it with relatively few lines of problem-specific code. We can use a lot of those off-the-shelf models that we talked about as kind of plug-and-play pieces, which make it so that we don't need that much engineering effort to kind of go from a whiteboard sketch to an initial feasibility study of whether this concept is kind of going to work. And so as a result of this, we increased the flight range from what we had projected on paper from about 82 kilometers up to about 250 kilometers here. With this resulting design here, which has the CAD model here, which was prepared by Julia. How do we get such a large range increase here out of this vehicle? Well, a lot of it comes down to coupled vehicle and trajectory optimization, which we hadn't considered. We had just initially assumed, okay, we launch at 30,000 feet, we're going to stay at 30,000 feet, and then once we run out of rocket engine propulsion, we're going to glide to the ground. It turns out that what you can actually do is fly on this boost glide trajectory. So initially, right after launch, you fly very, very high here. And then you basically act as a high altitude glider and you fly down the rest of the way. That means that you're less optimized for that dash condition at Mach 0.8, but you're more optimized for extending the range of this glide here. That's a synergy that we didn't consider before we had actually coded this and run in an optimization framework here. To illustrate that more, we can actually do things like multi-objective studies, which inform some of our decision making. So here we're plotting the total range of the vehicle here. On the x-axis versus the boost range of the vehicle. So how long it actually runs for that initial Mach 0.8 dash phase. And as you can see, some of our initial mental models looked a lot like this kind of missile-like design with minimal fins here. And that actually stems from just the way that we were conceptualizing the problem. But if you go to this high-speed glider, the trajectory changes, the wing design changes, you get much lower wing loading, and all of a sudden you can get a much higher glide L over D. And so that's a lot of kind of where the gains come from. And it illustrates the benefits of kind of looking at all of this together, even from the early design stages. And then, of course, the fun part of this is that we can take a model here, export it to CAD, add in a lot of the detailed design, build it, and then actually go and do a flight test, and then use that to kind of validate the model. So this is a good example or an illustration of taking an optimization model and then having it take on a bit of a life of its own in terms of being this digital twin which tracks your design as you're going through the rest of the actual build and flight process. Another example that's kind of fun is MIT Dawn, which is a high altitude long endurance solar airplane, which again, some other people in the room also worked on. Very cool project. Basically, we were tasked with keeping a 30-kilogram payload over the continental US for at least 6 weeks at a time. We looked at a lot of solutions, but ultimately solar airplane is what we ended up looking at here. And there are some challenges with that. You know, you need to station keep against winds, you need to survive the gusts on ascent, and just, you know, making sure that you can close the energy margin for overnight flight with batteries is also a pretty big limit. So one of our key early questions was, okay, so where in the world could we actually fly this? And if we change the season that we fly in, so which month we fly in, and the latitude that we fly at, how does the required size of the airplane change, right? So a smaller airplane means less aerostructural risk, it means less cost, it means easier prototyping. We wanted to kind of figure out what's the easiest place in the world to fly this and what's the easiest month to fly this in. And so, you know, intuitively, what you would think is, okay, sunny conditions make it easier to fly a solar-powered airplane, right? So you fly near the equator, you fly in the summertime. What we actually see is that the thing that matters most is the length of the night, because that determines the battery sizing. And so where you actually get the smallest airplanes is in the Arctic in the summertime because of the midnight sun effect. And similarly in the Antarctic in the wintertime, or in December, I guess I should say. And so how did we kind of do an analysis like this? Well, we formulated an optimization problem for that airplane, assuming some seasonality and latitude, right? And then we designed 2,400 unique aircraft for each point in a 60-40 grid and seasonality latitude space, right? To basically figure out, okay, what's the minimum wingspan airplane that you need to fly here if you have a rubber airplane, right? And the cool thing here is that because of the speed, you can actually do this interactively. So this, in total, if you massively parallelize this run on a high-performance computing cluster, executes in only a couple minutes. And so you can start to do this fast enough that you can do studies like this in real time while you're thinking about this with other engineers in front of a whiteboard. And so based on this, we identified some early missions of interest. You can see our initial science mission here in the rectangle here. And gained a lot of intuition about the design space that we otherwise probably wouldn't have gotten until later in the process. The other thing is that, you know, due to some of the methods about how the optimization solve happens, you get the design sensitivities for free. So how do things change as you change some of your assumptions? That's very, very useful information to have early on, especially as you're thinking about how to spend the R&D budget in different areas. Is it worth taking a motor weight hit if you get better efficiency? Questions like that. And then finally, you know, this model with a lot of excellent engineering work from Harvard, Electro.aero, and other people was actually carried forward into a first flight in September 2022, which was a very rewarding thing to kind of see this model kind of take a life of its own eventually. Let's see, we're gonna skip through some of these for time here. So I'd like to go into the contributions 3 and 4 of the thesis here, which is basically, okay, this is great if you can make a computational graph of the user's code. But what if the user has what's called black box code, meaning legacy code written in a different programming language, or in some other way where you can't directly access the internals of the code to make that graph? Well, there are a couple strategies here. In short, you know, if the model's smooth and you can provide gradient and adjoint and sparsity info, you can define a model as a new primitive, as basically its own operator, and throw it right into the framework, and then you're done. However, if you don't have that information, you may be stuck running it as a true black box, right? So just kind of finite differencing through that, assuming fully dense Jacobians, things like that. Or you have the option of making a surrogate model, right? So some kind of faster standalone model that's coded within a differentiable framework that you can swap in there. So here we're going to talk about some things, some interesting developments that come around these options. So the first thing we'll talk about is a strategy called NAN propagation here. And to motivate this, we're going to take an example model, which is actually taken from some of Prashant's work here through tazop.jl. This is a wing weight model. So essentially, it takes in 38 inputs, like the wing shape, material properties, and many others, and it spits out 37 outputs. Things like, you know, the weight of every component, stress distribution, weight distribution, things like that. And this is actually the reason we choose this model is that it's an interesting level of complexity. It's complex enough to be interesting, but it's not so complex as to be unmanageable, right? But also it's written in a different programming language, which means our only interface to this is basically calling it. We can't do any other tricks to it. We just have this as basically a pure callable. And our question is, okay, what is the sparsity pattern? Which inputs affect which outputs? The reason we want that is that if we have that information, we can still make finding gradients of this black box a lot faster. So how might we figure out which inputs are linked to which outputs? Well, here in our strategy, we take a representative input, which might be, say, the initial guess for an optimization problem. We basically make different inputs, which we individually seed with NaN value contaminants. NaN's basically a special floating point value, which stands for not a number. And basically these contaminate calculations as they fall through that. And you can basically exploit that handling to figure out which inputs are related to which outputs here. So you get an output here, and depending on which ones are NaN values, you can figure out which ones are linked internally. So what does that look like on this example problem here? Well, for this particular model, we've got all of our inputs on the columns here, all of our outputs on the rows, and every gray dot that you see here is basically an input-output link where we've established that that input affects that output, right? Now, what's the benefit of doing any of this? Why do we want to do this for black boxes? Well, basically, we can figure out that if two columns here don't interact, right, we can actually evaluate their gradients simultaneously. This is called Jacobian coloring. And it's, at least kind of the next best thing. If we don't have an exact gradient, we can at least compute the gradient more quickly now. So what does that look like? Well, if we go back and forth between the previous Jacobian and this Jacobian, it's literally a compression step, right? We're kind of taking all the columns that don't interact and we're squishing them together. And so what does this mean in practice? Well, it basically means that we can compute all of our gradients, in this particular case, about 50% faster. It's case dependent, but it's at least better than kind of doing a black box finite differencing. And the real reason that we're interested in this is that it works in basically any programming language. There's an IEEE standard, IEEE 754, which governs how NaN values are propagated through math, and pretty much all programming languages will respect this handling. And so we can do this in a way that's language agnostic. Now, one of the kind of caveats here is, okay, but what if we have branching code execution? So what if you have like an if statement hidden inside there where you can't actually determine, whether you traverse the entire code execution tree? Well, basically, you can't make any guarantees in that point, but we can make some heuristics that work pretty well. And one of those is that often those branching code executions come down to either Boolean or integer valued flags in engineering code in practice. And so you can identify type signatures of the code that you're running, identify which variables may trigger branching code execution, and preferentially loop through those and basically figure out if you've gotten the entire sparsity pattern. So for example, this wing weight model has a flag about whether there's a strut or not on the wing. And obviously that's going to fundamentally change the physics modeling. So if you don't have a strut, this is what the sparsity pattern looks like. If you do have a strut, it fundamentally changes. So going back and forth, you see most things are the same, but there are a couple columns and rows that swap here. So how might you actually fix this? Well, you might take a greedy approach where basically every time during execution that you see a new value on a discrete variable or something you suspect to be discrete, basically union that sparsity pattern with everything you've already seen and redo the Jacobian compression here. So in practice, step one, you evaluate it with your initial guess. If you ever see something new, you reevaluate it, you redo the sparsity pattern compression, and you take the union of that. And one of the benefits of doing this, by the way, so the traditional approach to finding the sparsity of a black box would be just taking a derivative and seeing which ones are zero. The benefit of doing this NaN propagation approach is that you're not fooled by accidental cancellation between different parts of your function. So just because a gradient is zero doesn't necessarily mean that that input and output aren't connected. However, the NaN propagation will pick that up. And on this example problem, we can see how the NaN propagation method finds the true sparsity pattern, but finite differencing doesn't. And so that's the reason why this is an improvement kind of over the kind of existing methods. Now in the thesis, there are some really hacky extensions to this, but I want to talk about one of them in particular because it's just really cool. which is basically that if you actually look at the bit signature of a NaN value in floating point, this is in floating point 32, you actually have about 21 bits of unused information inside there, in the sense that only this is required to actually determine whether it's a NaN value. Everything else is not used. What does that mean? Well, it means that basically you can tag individual NaN values to make them uniquely identifiable. And then you can actually seed multiple uniquely identifiable NaN inputs into the function at the same time and fundamentally improve the scaling here. As opposed to being order of n scaling with the number of inputs, you can actually, evaluate multiple columns simultaneously and get fundamentally better scaling here. Now, it's not quite order 1 scaling because of certain effects that happen when you get NaNs that interact, but you can, in an average case, for some definition of average, you can get close to n log or log n time, which is a substantial improvement over order of n time. The final contribution we'll talk about today is basically, okay, so what's another strategy you could use to handle black boxes? Well, you can make surrogate models. And this is one particular surrogate model that we use for a black box tool, which itself is not differentiable. And in particular, we're using XFoil here. XFoil, probably familiar to most people in the room here. It's a bread and butter of kind of 2D aerodynamics analysis for airfoils. But one thing that not everyone might realize is that it's actually not smooth. And fundamentally, it's not smooth because of certain modeling assumptions. Meaning that if you try to do gradient-based optimization on XFoil, it won't work out of the box. There are certain things you can do to kind of get around that, but it's actually, when you zoom in, kind of ragged here. This is a figure taken from a paper from some colleagues at the University of Michigan here who were studying it for design optimization purposes. So what's kind of like a practical example that might motivate us to look at this? Well, let's go back to Firefly here, which we talked about. Well, Firefly operates at very low Reynolds numbers, about 500,000, right? And a Mach number that's well into the transonic regime, close to Mach 0.8 here. And because of that, you get two competing effects here, right? So an airfoil that's really good at transonic cases is going to look like this. This is an off-the-shelf airfoil. An airfoil that's good for low Reynolds cases is going to look like this. And they have fundamentally different pressure distributions motivated by directly opposing factors. So if you have to operate at both of these conditions, it's not necessarily obvious how you want to design the airfoil. And the problem is that the performance of Firefly is exceptionally sensitive to how you do this, and the trajectory is coupled with it. So you can't separate this out as kind of its own problem that you pre-solve. So that motivates bringing in, an advanced tool to kind of look at some of the finer details of airfoil optimization, like XFoil. Although in this case, we can't do that because it's a black box function. So how do we get around this? Well, here we trained a model that we call NeuralFoil, which is basically a hybrid of a neural network on the inside and then a bunch of physics priors kind of embedded into that, as well as extrapolation to no limit cases. And this is trained on about 12 million XFoil runs, which in total is about 2 or 3 days of computation on a high performance computing cluster, although this only happens once. And so this model basically takes in all the things that you'd expect: the airfoil shape, angle of attack, Reynolds number, Mach number, turbulence parameters, control surface deflections, and outputs, both bulk outputs, lift, drag, moment, things like that, but also enough information to reconstruct the whole flow field, including the boundary layer behavior. And so we can compare the accuracy of a model like this, which does physics embedding, to something like XFoil. Here we're comparing it on this HALE 03 airfoil. This is actually the airfoil that was used on the Dawn solar airplane. And the cool thing about this is that that airfoil was developed from scratch, not from any of the airfoils that we use to train NeuralFoil. So this is a good generalization test, basically. How well does it do out of sample, out of distribution on a new airfoil? And it tracks pretty closely. So XFoil here is, in the black dots here, and NeuralFoil is in both the dashed line and the solid line. Within NeuralFoil, we have 8 different models that are basically a speed accuracy trade-off. And so that's what you're seeing here, different model fidelities here, and they're a different accuracy. The median absolute error of drag on airfoils you haven't seen is about 2%. And that's actually including post-stall, transitional, high curvature cases, all the way out to, I think the max is about 28 degrees angle of attack. So most of this error is actually dominated by some pretty out there edge cases. Another way to show generalizability is that none of the training airfoils actually had any control surface deflection whatsoever. So we can test, okay, if we give it control surface deflections, which it's never seen, how does it do? Is it actually learning the physics, or is it just memorizing the input, data space? And the cool thing is that even out to 40, 50 degrees deflection, you actually get pretty close agreement with newly run, X-foil solves here. Again, there are, certain model assumptions that you start violating at this point, but you can, it's a good indicator that you're actually learning underlying physics as opposed to just the training data here. One thing, and kind of a, my chance to kind of get on the soapbox, is that a lot of times in these kind of machine learning surrogate modeling studies, you see these really good speed ups, but not without controlling for accuracy. And the reason that that's a problem is that oftentimes if you have a conventional solver, a traditional solver, you can also get speed ups just by dropping the discretization resolution, which will drop the accuracy, right? So you really have to do like an apples to apples comparison of like, is this actually faster at the same level of accuracy or not? So here what we do is we test over a database of airfoils, a different database than the training one. And Xfoil here is used as the ground truth. We run Xfoil with the maximum number of panels allowed as the ground truth. Then we take Xfoil and we run it with fewer and fewer and fewer panels, all the way down to 20 panels. And we can do a speed versus accuracy curve here. And our goal is to kind of get to the bottom left of this plot here, right? And then we can run NeuralFoil on the same airfoils, the same cases here, and run all the way from our smallest models all the way to the biggest models. And again, we have that speed accuracy trade-off here. But we see that, in all cases, you can get a speed up by actually using a machine learning surrogate here. And not only that, one of the benefits of NeuralFoil is that you can vectorize evaluation simultaneously. It's a lot of large kernel operations, and it's guaranteed, it's a static execution path, unlike something like Xfoil, which has a convergence criterion. So because of that, you can analyze multiple airfoils, multiple aerodynamic cases simultaneously. And when you do that, you actually get a much, much larger speed up here. In fact, it's close to 3 orders of magnitude in this particular test case. There are some other things that the thesis goes through, for example, compressibility modeling here in NeuralFoil. The drag into the transonic regime isn't that accurate, but the prediction of where transonic flow starts is pretty accurate because that's based on the physics modeling itself. The motivation there is that if you're doing design optimization, your optimum design is probably not deep into the transonic regime. So you care about predicting when transonic flow starts, but once it's started, you're probably not that concerned about operating deep into that regime. So to kind of bring it out and talk about, what can you do with this? Well, if we go back to our Firefly airfoil case study, right? Based on this analysis speed and continuity, we can start to do airfoil and airplane co-design optimization. So for the Firefly airplane, just a simple study that we can run here is, okay, if we have our airfoil shape, what if we just maximize it for max L over D at 0.8 and 500,000 Reynolds number? And we do a multi-point optimization across basically a 6-degree angle of attack range, about some arbitrarily selected range, in order to mitigate some of that over-optimization. And you can see that this can actually be used to drive an airfoil design optimization study. So what does this get us in practice? Well, okay, so if we've got our Reynolds number on the x-axis and our Mach number on the right axis, remember we said that there are some airfoils that do well at high Mach, but not at low Reynolds. There are other airfoils that do good at low Reynolds, but not at high Mach, right? And we want to kind of do both. And this shows that we kind of optimize to push up into this space here. Now, in this particular case, we probably want to add some thickness constraints on this. This is actually, you could maybe make this out of like a single layer carbon or something like that. But there are other constraints you'd want to bring in there, but it's a demonstration that you can actually start to achieve some of your aerodynamic objectives by optimizing these together. One final case study with this NeuralFoil tool is, okay, like if you're optimizing through a physics model, you need to be careful about adversarial optimization. Basically, any model errors are going to be exploited by your optimizer. And so you want to know, okay, if you get an optimum result, is it actually real, or are you preferentially going to regimes where the model is invalid? Because that's where it can eke out more performance. Now, there aren't that many airfoil design optimization cases in the literature that have well-documented formulations. But if you're looking for an expert designed airfoil with a well-documented problem, Mark is one of the best sources for that. So this is an airfoil that Mark designed before I was born. For the thanks for that. For Daedalus, which is still to this day holds the world record for longest endurance human-powered airplane, and is really a well documented problem for a very particular aerodynamic operating case. So we can basically formulate this problem and see, okay, like how close can we get to that, right? And we can run this in 3 studies. First, we can do an airfoil that we optimize using NeuralFoil. Second, we can have the red airfoil, which was what was actually flown on Daedalus. So that's kind of the actual airfoil. And then green is what do we get if we just directly optimize through Xfoil itself? And again, there are those gradient issues which prevent you from really getting to the optimal result because of the smoothness issues near the optimum. And what you end up seeing is actually that the NeuralFoil airfoil and the expert design airfoil are pretty close here. There's about 1% drag difference there that you can kind of eke out. So, but you've captured most of the low-hanging fruit there. And with anything like this, whether it's an airfoil, an airplane, you're never going to have perfect push-button optimization where you just hit the button and then you go build it, right? But something like this is a great starting point for further expert refinement. If you're trying to design an airfoil and you can start from something that's pretty close to it, rather than starting from scratch, that's still a huge engineering time savings. So that's kind of the benefit here. So to kind of overview, so the thesis contributes in basically 5 different areas. The first one is a code transformations framework for MDO paradigms, and what it looks like if you build on top of that, some of the opportunities as well as some of the challenges with that. Secondly, it fleshes that out a little bit more by adding some physics models, which are useful if you kind of want to do practical studies or jumpstart future applied research into this area. Third, it presents a new method for sparsity tracing through black box functions with asymptotically better performance than existing methods. Fourth, it presents a strategy, a demonstration of how you can use physics-informed machine learning surrogates for black box modeling and achieve essentially minimal loss of fidelity and still something that you can run online with the rest of the optimization study. So the key takeaways here, well, first of all, code transformations can make optimization methods, advanced methods, more accessible and practical. But if we're going to do that, we really need a dedicated focus on that ease of use for, if we actually want to get industry to use these tools. And then the second part is that AeroSandbox is a proof of concept design optimization example or a framework example of how you could use this. And despite being kind of a proof of concept framework, in the 5 years that this has been public, at least, it's seen a lot of industry interest here in terms of use cases. We're approaching 1 million downloads here. And the interesting thing is that actually a lot of the users, maybe a third of the users, are not in aerospace. Again, a lot of the stuff that we've talked about, the traceable physics models are aerospace specific, but the underlying optimization methodology is broadly applicable to engineering design optimization, whether it's boats, bridges, cars, things like that. Yeah, so many thanks to a couple people. First of all, the people who gave me money. NDSEG, BAE Systems, MIT Portugal, and then the Supercomputing Center here at MIT. Secondly, I'd like to thank a lot of open source contributors, both directly to AeroSandbox, but also to the underlying key software stacks. It really is just this kind of, perpetual building on top of buildings, right? And like none of this would be possible without many, many, many people who came before that, millions of code hours that people put in. Closer to home, I'd like to thank my thesis committee and readers, especially for slogging through, the document recently. And then I'd like to thank, my friends, lab mates, family, and loved ones, especially Marta here, who has been fantastic these past couple weeks getting ready, and all of you for attending. So thank you for bearing with me while we go through quite a lot of material and not that much time. So thank you very much.
So, hey, thanks, Peter. This is great. I'm not, Mark, can you handle managing questions? Because it's hard for me to do it remote. Or are there questions there? Or Peter, do you want to do it? Yeah.
Why don't you pick up?
Okay, well, I guess we'll start with the committee, maybe,
Anyone, really.
Okay. or anyone. Johannes.
You knew this one was going to come for you. Really great work, Peter. And I think the C1 continuity embedded in all of the models, that's like awesome. And more people should be doing that. So IPOpt is a local solver. And so that depends either on having good initial guesses or the lack of multimodality in your underlying models. So how do you get around that? Or do you have some intuition? Is there multimodality in the problem? And did you start near a good initial guess? Or is there a lack of multimodality in your problem? And you're just gonna find it.
That's a great question, and I think a two-part question. So the first part of that, let's talk about the initial guesses. So one of the nice things is that you can do automatic problem scaling, right? Which really diminishes the impact of a bad initial guess. So for example, in this comparison here, where we're doing the n-dimensional Rosenbach problem, the initial guesses are actually started from a really awful distribution, about uniform from -10 to 10. I mean, looking on this chart here, right here, you're way off the optimum. And again, here the condition number of the Hessian at the optimum here is about 2,500 in 2 dimensions, and gets worse in higher dimensions. So that's an example of kind of what happens if you have a bad initial guess. Well, it turns out that if you do a lot of auto-scaling heuristics, you can kind of mitigate that to some extent. Even on applied problems, we find that usually if you're within about 2 orders of magnitude plus or minus on a value, you're pretty likely to converge. And the second part of the question is about multimodality. That's, I mean, unfortunately,
We need to find that, I'm not sure.
Sure, okay. So, you're doing optimization, which at a high level, you're trying to find the minimum of a function, right? So you're kind of rolling a ball downhill. That works great if there's only one bottom of that hill, right? But if you have multiple valleys, right, which one are you going to go to? You may go to a valley which is low, but not quite as low as the true bottom of the valley. And so, unfortunately, there's no good answer there, because any strategy which tries to, explore multiple minima is inherently going to be slower. Just the no free lunch theorem, right? However, I'll lean on a quote from Professor Martin's textbook, which is a great textbook, which is that, oftentimes in applied problems, the minimum that you find in aircraft design is unimodal, right? There are edge cases, an example would be like in DBF, where you have multiple competing scoring functions. You can get multimodal stuff where you go preferentially towards one or the other. But in practice, most of the time, it's close enough to unimodal that it's not a huge problem. Bjorn.
So in this case, AeroSandbox is faster than gradient-based optimizers like the BFGS. And the way I understood it is most of that runtime increase comes from that optimization of the computational graph that you're doing. Can you explain a little bit more which optimizations that are?
Yeah. So I should clarify that the underlying, so AeroSandbox is a tool for formulating optimization problems. It's not an optimizer itself. The underlying optimizer, which should get the credit, is IPOpt, right? However, when you do that formulation, like I said, there are things that you can do to prepare that computational graph, or prepare how you're going to do things like constraint evaluations in a way that's faster. In particular, one of the things that we can do here, well, there are 2 things that we can do here that are faster. First is automatic differentiation as opposed to finite differencing, right? So you're going to get speed ups both in terms of how quickly you can evaluate that, but also in terms of gradient accuracy, which on a problem like this, which has a really poorly conditioned Hessian, makes a huge difference. Just a tiny error in your search direction is going to put you way out of that valley, right? The second thing that you can do here is automated sparsity detection. So if you squint here, this is basically a summation of adjacent terms. So if you have, if x is a 100-dimensional vector, this is basically a summation of x1 and x2, and then the next iteration would be x2 and x3, x3 and x4, right? So the only variables that actually interact here are x1 and x2, right? And so one way to think about that is that the Hessian of this is actually going to be very, very, very sparse, right? It's basically going to be a diagonal and then one diagonal below it, right? And because of that, if you can find that sparsity and do Jacobian compression before you evaluate that exact Hessian, it becomes a lot faster. So those are the two speedups that in this particular case are making the biggest difference.
So are you effectively creating a Newton's method? They're discovering Newton's method?
Sorry?
Are you effectively discovering Newton's method? Is that what I'm hearing?
What do you mean by that?
Well, so you're saying that you are doing an exact linearization, but I'm guessing BFGS and LSQP
So it's
are not
getting
doing the-
getting an exact Hessian, but it's not just doing a Hessian update step. It does do a line backtracking. Right.
I guess let me ask you this question. I'll ask it this way instead. Where would IP-opt be on here without AeroSandbox?
Well, IP-opt itself doesn't compute gradients, right? So how you compute gradients is going to make a difference. IP-opt would probably be
Suppose
pretty
you
close
use-
to this line if
I
you
mean,
define
you
a
did-
differencing.
So did you use exact gradients for SLSQP and LBL?
No.
Oh.
no.
Okay. So
Those
you
are
set
finite
them-
difference gradients.
Okay, so you set them up for failure.
Well, in a way, I mean, that's what you'd be doing with black box optimization, right? I mean, you can't assume you have gradients for black box optimization.
Oh,
If
okay,
you
you got the
do,
black
then
box.
all of a sudden it's an analytic gradient method.
Okay.
In which case it's a different conversation, but for black box optimization, you don't have this.
Got it. So, but AeroSandbox, you're still
It does
doing,
have exact gradients.
even on the black box.
Even on this test, you know. Well, this isn't, I mean,
So you use the NAND thing to get the exact linearization of the black box? Or this is now,
No, this
now
is-
you've confused me.
so to AeroSandbox, this is not a black box.
Oh, so you didn't, so AeroSandbox is not treating this as a black
Yeah,
box,
this
but
isn't-
the other ones are treating it as a
This
black
isn't
box.
saying that this is a comparison on a black box problem. This is a comparison of a black box optimization paradigm to a more specialized paradigm. In the same way that you might do like a comparison of like GP-kit to, you know, the same problem but solved
Okay,
with, you know.
so if I
black box
took
methods.
BFGS and I
Yeah.
gave it gradients, I can
Yeah.
differentiate this function, I gave it to it.
Then it would be closer to this.
Okay,
Assuming you computed those gradients with automatic differentiation, so you lose the order n scaling.
automatic differentiation or hand differentiation, as long as you
Either one,
differentiate it.
right,
yes.
exactly. Yeah, assuming, yeah.
So I have a related question, which you just partly answered. But the conditions that you need to be able to sort of plug AeroSandbox into these problems, are those the same conditions that would hold to be able to do automatic differentiation? So
Yes.
in other words, like, is there a line missing on this graph that Marshall was just asking you about? Because for any of these problems, you would have been able to do automatic differentiation and sort of let the black box optimization methods actually have.
I mean, yeah, I mean, I guess you could add a line on this graph for IP-opt with exact gradients. That would
This
be
is what
like,
I was asking.
yeah, that
Yes.
would be like another.
Same thing,
Right, and it
I
would
would
be
compare
probably
BFGS.
somewhere in between.
I guess
here.
what I'm asking is not just for this problem.
Yeah.
If you have a problem, you have a set of black box codes and you're coming in with AeroSandbox, could somebody else come in with automatic differentiation always? Or are there additional things that are needed to apply AD to these problems?
So, okay, so first, I guess what's required to use AeroSandbox with the stack? Well, first of all, it has to be written in Python. The user code has to be written in Python, or the problem has to be written in Python. And it has to be written using the specialized numeric stack, which basically means NumPy, SciPy, or, you know, our ability to hot swap that in. You can do automatic differentiation outside of those constraints, right? So there may be a situation where, say, someone has a Fortran model that they want to optimize through. And the easier thing for them to do is to use Tapenaid, a Fortran AD tool, to get the gradients and then plug that into IP-opt versus port the whole thing into Python and do that. The performance is going to be about the same, right? Because of that. Yeah. However, you know, the value proposition is that if you can do that with what looks and feels like native NumPy code, which, you know, a lot of engineering analysis could be written in, then maybe the actual user experience for the end user to get to the same place is a lot easier. But yeah, performance-wise, it probably would be similar. It's hard to say whether it would be closer to this or closer to this, but it'd be, you know, it'd be somewhere in the middle. I don't know how much the sparsity plays into it. It's basically a big question. And it depends whether your AD is assuming that you're doing Jacobian compression or not. So.
A couple more questions here. So first of all, you did a great job on the thesis. You packed so much into the thesis document, and then you packed a lot in today to the presentation too, which is amazing.
Someone should have told you to stop a year ago.
So you did a really nice job in giving the intuition as to what's going on. Like for example, with this plot, this is an unconstrained problem. Can you give us a little bit of intuition about the role of constraints and how everything you do maybe scales with both the number of constraints and the complexity of the constraints? And like when you were talking about the multiple valleys, right, that can happen when you have a non-convex function, but it more often would happen in a design problem where you have maybe constraints that cause you to jump around.
Right.
So you could talk a little bit about how everything that you're doing behaves in those situations, and whether you've seen some problems where constraints are really driving strange design space behavior.
That's a great question. So to start with, the objective and the constraints are kind of equally difficult parts of the problem in terms of the computational speed. That's because it's using an exact Lagrangian Hessian, so the objective part. And then it's also using a constraint Jacobian. So those are both matrices, and so you're scaling in terms of like how slow are those to compute. It's about the same because they're both matrix computations. In terms of let's see. So question was about
How you show a lot of plots in terms of how well you do as a function of problem size, number of design variables. What about number of constraints? And I know it's more amorphous, but sort of complexity of the constraint space.
Yeah, okay. So in general, the limitation, you don't get fundamentally, the performance hit from like an additional variable and an additional constraint is roughly comparable in the sense of, like the Firefly problem, you're roughly, 4,000 variables, 8,000 constraints or so, and it's not like having the number of variables but keeping the same number of constraints or vice versa would, fundamentally change the scaling, more than the other, right? Where you do get into, interesting thing is that oftentimes if you have an optimization problem that won't converge or something like that, the problem is in the constraints itself in terms of the formulation. And so because of that, one of the tricky parts, not so much the computational speed, but in terms of the usability, is how can you figure out which constraint is actually causing the failure? So if a user has a problem that's, where they've posed an infeasible problem, there is no feasible space, right? Which constraint do you actually apply blame to, right? Because it's not like any one constraint is doing that, it's the combination of constraints that does that. And so one of the areas of kind of active work right now is basically improving, okay, like how can you report that? Basically what we do is that you figure out the norms of each of the constraints and you put out the indices of, which constraints have the highest violation, right? And then you actually map those back to, whenever a constraint's declared in code, you record which file and which line of code that came from by basically self-inspecting. And then you can print out which line of code the user wrote is actually corresponding to that constraint that was violated. So that's, when it comes to constraints and the challenges around it, I think that the big challenge is not so much the computational performance, it's actually in diagnosing what went wrong when there's an infeasible problem posed. And that's something we're sort of working on right now. Yeah.
So you looked at Jacobians of the codes themselves, but not so much the objective function. Is that fair to say? Because they're not the same thing. I mean, normally you formulate an objective function from the outputs of code. That's the usual.
Right.
Right. So don't just optimize drag, you optimize some weighting constraints. Right. So and very often, you never mentioned the word Pareto at all, or multi-objective.
Yeah.
So how does all this machinery, does it help you there or not? When you look at multiple objectives like sparsity.
Yeah.
Right, that's gonna not, is that
Well,
useful when you
it's
have
still
10 different objectives that you want to look at?
So that's a good point. If you're weighting different objectives, in general, every objective that you add, if you have like say a linear combination of objectives, in general, that Lagrangian Hessian is going to get less sparse. So they're just adding more pieces together in general, right? But just to kind of go back, the two things that you're kind of giving to IPOP are basically a callable or a function handle that's, efficient to call the Lagrangian Hessian, given some duals and primals. And then some function handle that's efficient at calling the constraint Jacobian. So in all problems, you do get both of those, right? To go to multi-objective stuff, let's see. So let's say like on a problem like this here, where we're kind of doing the trade-off of total range versus boost range here. Within AeroSandbox, kind of the formulation framework itself, there is no built-in weighting for multiple objectives. However, what you can do is you can sweep over different parameters. So you can you can solve for one point, you can use both the primals and the duals as the initial guess to the next one and sweep through some assumption about what your weighting might be. And that parameter that you're sweeping over could be some weight that controls kind of the linear combination of objective 1 versus objective 2. So that's a way you could pose it. There are other things you could do, like, do like a box constraint, or like a, basically move a constraint boundary, through this space to kind of sweep through what's the minimum total range you're willing to accept, and kind of build up your Pareto frontier that way. And because you can reuse your previous solutions, it's faster than doing just like a blank solve because of that. However, that's more on the problem-specific formulation side, and so that's kind of left up to the user in terms of exactly how they want to implement like a multi-objective problem like that. Johannes.
If I may, another.
Yeah.
So how well does the user need to understand the design space? And what I mean by that is, to what extent do they need to understand the lower and upper bounds for the design variables and give those explicitly? And how does that impact how well AeroSandbox?
That's a good question. So in general, for most things, you don't need to provide upper and lower bounds until they get to the point where it's physically infeasible. So if you have something like a chord, like the tip chord of a wing, right? You probably want to put in like a lower bound constraint that doesn't go negative, right? Otherwise you get some, it breaks a lot of the physics models. Another example, and maybe a more subtle example, is with something like the lift coefficient. Let's say that you're optimizing like a trim condition, right? You probably want to put in a constraint that the lift coefficient has to be positive if you're going for like a lift equals weight constraint. The reason for that is that if the lift coefficient goes negative, the sign in the Jacobian flips, and it'll actually try to decrease the airspeed, right? To make that less violated. Whereas in practice, what you actually need to do is make the lift coefficient positive again. So until you get to something that either results in a sign change in some downstream constraint, where it's going to start searching in the wrong direction, or it's like, obviously physically invalid, that's kind of where you want to start adding in hard bounds. Yeah, but until that, usually you don't. In fact, usually if you leave it unconstrained like that, that's where you get honestly some of the most interesting results out of a tool. If you find that, say, like a wingspan is growing without bound, usually that's like a really fruitful avenue to kind of bark down and figure out why you're getting that, because it means that there's something about the problem that you're not fully kind of expressing in code, or it's an avenue that you could exploit for better performance.
Hey, Peter, I have a question, but before I do, I want to check and see, make sure Joaquim doesn't have a question.
I have many questions.
Okay.
Can you hear me okay? Can you hear me?
Yeah, we hear you good. Yeah.
Great.
Yes.
All right, so I wanted to follow up on the question of local minima, because it's, I guess, one of the questions I get a lot. I get it so much that my students got me. Can you see the camera?
Yeah, we've got the camera.
Yeah, so they got me a hoodie that says, "Ask me about local minima." So you mentioned that, yeah, I did say that in aircraft design, basically you get fewer local minima than most people expect. The main message that I put in the book is really that a lot of times people worry too much about local minima. So my question is to you, Peter, did you see any credible multiple local minima for any of the given problems you solved?
So for these, that's a great question. For these problems that we talked about today, no. But one place that I did see multiple minima in the wild recently. Where I was looking over some of the code for the design will fly students here, which was using this same stack. And in that particular case, I mean, this unexpected, but basically, you know, the mission score is mission 1 plus mission 2 plus mission 3. Missions are going in very different directions. One's like light and fast, the other one is slow and heavy, right? And so in that particular case, you know, with the right kind of formulations of those problems, like you're going to get yourself into a case where it either goes all for mission 2 or all for mission 3, and not so. But like you said, I mean, that's kind of a contrived case that comes from this formulation. Unlike real world industry problems, I agree with you. I haven't seen really any cases where it's been significant like that.
I mean, you definitely need to consider the possibility. It's just, again, in my experience, happens a lot less than people, many people imagine. So anyway, good. So, so on slide 19, I agree with Marshall. I think the comparison with, you know, when you write BFGS, yes, a lot of people do use, most people would use finite differences, but a lot of people use analytic derivatives. So I think that's confusing. You need to qualify that a bit better. All right, so you mentioned, of course, you use, so first of all, let me start, they did an amazing job, a lot of work and in quantity and quality. And I think, yeah, I'm really impressed. So congrats. When you talk about differentiation, right? So you have the traceability, differentiate everything. During the presentation, in the thesis you mentioned this, but in the presentation you didn't mention, I don't think you mentioned forward and reverse mode. Would you like to explain that a bit more?
Well, there's a
Oh, there you go, yeah, you did have it there. So do you use the reverse mode throughout, or is there any situation where you use forward mode?
Yeah, so there's a heuristic for it. It depends what you're evaluating. For example, for like, you know, let's say that you're evaluating like the Hessian, right? Typically that's going to be forward over reverse in the implementation. If you're evaluating like the derivative, or if you're evaluating like a gradient of like a scalar though, right? Sometimes you do in different places here. There's a heuristic, which is basically, it kind of goes back to like, you know, number of inputs, number of outputs, but there's an exception where, you know, forward mode tends to be faster even if you have more inputs than outputs, forward mode tends to be faster if it's not extreme, right?
Mm-hmm.
Yeah, it's a very.
Is this done automatically then, this choice?
It's all a heuristic and it's all automatic. Yeah.
Okay, great. All right, if you go to slide 48, you got a comparison with the expert, designer, and NeuralFoil, actually, where you have the drag polars and airfoil shapes for, yeah, there. It's, I can see number 84, I guess. Yeah, so the shapes are pretty close between the NeuralFoil, Xfoil, and expert. Of course, I suspect the expert used Xfoil. But the polars of NeuralFoil look closer to the expert. But NeuralFoil is supposed to be a great model based on Xfoil. So what else does NeuralFoil know that Xfoil doesn't know there?
That's a great. The first thing is that they're analyzing different airfoils, right? So the blue line down here, blue polar, is analyzing the blue airfoil. The green is analyzing the green airfoil, and there are shape differences between them. So it's not.
But this was done NeuralFoil optimized, the Xfoil optimized. Basically, you have optimization with Xfoil and optimization with the NeuralFoil surrogate.
Yes.
And if the NeuralFoil surrogate is close, you know, very close, you showed previously very impressive matching with Xfoil. How can it get the expert design, closer to the expert designed airfoil. I don't get it. I would expect the blue and the green polars to be on top of each other, given the results you showed before.
Reason is that the green polar is analyzing, like you said, it's analyzing the airfoil design with X-foil optimization.
Yeah.
But analyzing X-foil itself is not well posed because X-foil is not smooth if you zoom in enough, right? So
Well, if you start with different starting points, right?
yeah, so the green airfoil is basically X-foil getting stuck in a local optimum because the gradients aren't smooth in X-foil.
I think something you might clarify this a little bit. It's like, oh, when you say X-foil optimized, using X-foil analysis, what is that exactly? Is that like there's not a built-in function you're
Yeah,
using, right?
that's like a gradient-based optimization algorithm built off of finite difference in X-foil.
Okay, so if you go back to the plot, that plot that Eitan did in his paper, if you go back more, so here you got great matching, okay. If you go back to the paper that I wrote with Eitan, you had a plot showing the C1 discontinuities, right? So, yeah, it is a case you get local minima, you'll get stuck there. Now, if your NeuralFoil is such a good match to X-foil, how does it avoid these discontinuities? I mean, if it is so good, it would basically.
Well, it's like 1 or 2% good, but it's not like 0.001% good, right? So it does go over the discontinuities, right?
Okay, I guess I'd like to see this same plot, but for NeuralFoil.
That would be interesting to see.
Yeah, because I buy it, it's probably smoothing things out, but how and how much, I think is an open question.
Is that, so NeuralFoil is actually C infinity continuous by construction. Activation functions that it uses, it actually is infinitely differentiable, which means that even if it were trying to learn a model that was not C1 continuous, like
Sure. No, I get that, but you can zoom into that peak and smooth that out and still have multiple local minima.
Yeah.
And still get stuck, because if you have very high curvature somewhere, that's as good as a C1 discontinuity.
We could fix X-foil.
Yeah. And in fact, there are, for example, like Shun's work with intermittency approaches actually does make X-foil C infinity continuous. So this is an example case. It's not actually a limitation of the X-foil methodology. It's just how this implementation. It's a good example case for what would you do if you had a discontinuous underlying function.
One more question, Peter. You say that the approach is physics informed, but I did not see what part of it is physics informed, because what I see is a surrogate model of X-foil.
Yeah. So, okay, so that's a great question. So the physics informed part comes in 2 ways. The written thesis goes into more details about that. The first one is that when you do the parameterization, whenever you construct a vanilla neural network, a forward parameter efficiency, the easiest function for a neural network to model is just an affine function, right? And anything that you do beyond that, you're basically giving up parameter efficiency to achieve that. So what you want to do is make it so that you want to use an encoder and a decoder such that the input-output mapping is as close to affine as possible, so that you get the most parsimonious solution without using all your parameters to model things that you could just otherwise model with, say, a power law, right? And so one of the ways that kind of the physics-informed part comes into this is in transforming or encoding the input and output spaces into a latent space where the mapping between those is very close to affine. So for example, a lot of, say, if you wanted a simple drag model of airfoil, it's turbulent model, it's going to be, RE to the -1/7, the turbulent regime, that's a ping law, right? And so if you put some of the parameters in log space, or you transform them in different ways, you can actually make that affine. And so the parameters get transformed in a way that makes that happen. The second way to get physics-informed structure embedded into this model is by embedding symmetries. So for example, if you train a neural network on a big airfoil data set, and you analyze a symmetric airfoil, you might not get that lift exactly equal 0. It's learning a model, but it doesn't know that that's actually a symmetry condition. But you can embed these symmetries into the model architecture in certain ways where that's actually structurally guaranteed to happen. So you
Yeah. Peter, I saw that sine and sine alpha squared. I thought that was a clever way to do it. I just don't see that as physics-based, but I'll defer to a machine learning expert.
Fair enough, yeah.
A final observation, and I think, if possible, I'd like to have a separate meeting with you because I have more questions, and I think it got me thinking about a lot of things. Is a term like code transformation that you define well in a thesis, but it's not clear if that's your definition or if it's a standard, widely accepted definition. Which one of those is it?
So I've seen people refer to these techniques as scientific machine learning techniques together, right?
Well, no, I mean, again, I'm not an expert on machine learning, but yeah, NeuralFoil is using neural networks, but I wouldn't call all this as machine learning.
SciML is a bit of a misnomer, but people do use SciML to refer to, a lot of things that, in my opinion, are not.
Well, I don't know. Is OpenMDAO SciML then, or yeah, I don't. Well, that's a bigger a discussion for another day. But anyway, I have more questions, but in the interest of time, I'll leave it here. And again, congrats on a really nice thesis and really stimulating. Thank you.
So Peter, I want to ask my question. So you motivated the thesis at the beginning. One of the things that you mentioned was the issue of reviewability. So use a technique like this, you come up with a design, and you now present it. So but you need to be able to interpret it from the outside, from the external review outside. Can you talk a little bit about where you are on that? Because that didn't show up very much in
Yeah, definitely.
what you said. Yeah.
This entire kind of graph, that is probably the hardest step, right? Is like, how do you take your results and actually kind of make them interpretable to people other than those who use it? One of the kind of strategies that we have that's already kind of useful is checking sensitivities, right? And so it's one thing to get to a point design if you can check whether you're in this very, very sensitive condition versus whether you have something robust. That's a step towards checking whether you've kind of over optimized or whether you're kind of in not getting too deep into the weeds. Beyond that, some of the things that we were talking about with constraints, where you can actually point the user, okay, you've got like this bag of numbers, this vector of constraints, how violated, how satisfied are they, right? Being able to actually map those back to the line of code and say, okay, which constraints are driving, which ones are not driving. That's also pretty useful in terms of determining, what is actually shaping the design, right? Typically, if you look at those constraints, and it may be only, say, 10% of those that are actually tight at the optimum. And depending on which 10, it may tell you, are you in the part of the design space that you expected to be in, or have you missed something that you didn't intend to? So,
but how do you assure you haven't made a sign error or a factor of 2, some coefficient error inside the problem? It's so you've tightly optimized it and whatever. So how do you know that?
Yeah, that's a great question, and honestly, I don't think there's an answer there. I mean, if there's a typo, you just kind of need to go through with like a fine-tooth comb and do your best. Yeah.
I mean, part of it is cross-checking against known solutions or something like that. But yeah, I think that continues to be challenging. Okay, thank you.
Kind of look at the, oftentimes the nice thing about aircraft is you can kind of look at the final design and if it looks weird, it probably is weird, you know? And so there's some amount of, as Bob would say, that looks about right that you can use to kind of figure out whether you're really going off the rails. But you know, as we were talking about, there are of course all the more subtle things that are harder to catch and can be big problems if you don't. All right.
One question I had about airfoil optimization in NeuralFoil. So my understanding is that when you do that kind of optimization, you're using something known as the Colfin parameterization. Is that correct? Can you speak a little bit about the advantages? Can you speak a little bit about the advantages of that relative to, let's say, just using the points?
Okay, yeah, that's a good question. So what we're talking about here is if you're doing this airfoil optimization, typically this airfoil is defined by say 200 points or so, order of magnitude. But instead of optimizing on those individual point locations, we're actually using mode shapes here, right? And this particular family is called a CST, or the Colfin distribution. You know, the reason to use a family as opposed to kind of the raw points is that you have some intuition that a lot of the changes that you're going to want to make to the design are not going to introduce very sharp local regions of curvature. Or if they do, they usually correspond to very local minimum stuff that you actually don't really want in the first place. So in some level, you do want to go with some kind of parameterization, some kind of lower dimensional parameterization than actually optimizing in the 200-dimensional, you know, input space of points.
Peter, sorry to interrupt, but you know, as we know, we use FFDs. We use about 20, and that's about enough to get as much out of the drag as possible. And yeah, so that was not 200.
Themselves versus a mode shape variation, of which FFD is like freeform deformation.
Hey, Peter, your mic has gone bad.
Let's see. Testing?
We can sort of hear you. Okay.
Try muting and unmuting. Testing? Is it maybe over here? Okay.
That's better.
Okay. All right. So basically, you know, if you optimize in a high dimensional space, very, very high dimensional space, you're not really gaining that much. So you want to optimize in some lower dimensional space. It could be FFD, you know, and somewhere in the order of say 2 to 40 shape variables per airfoil, maybe somewhere on that order, typically, right? There are lots of different options for different shapes that you can use. CST tends to be one of the most parameter efficient shapes in terms of can it capture things. There are some challenges to it, like the fact that, you know, there are globally supported mode shapes as opposed to having a local support. And so, you know, you can get some things where you get like kind of large changes in CST space, but not actually large changes in geometry space and things like that. But overall, when comparing different options, it tends to be one of the most parameter efficient.
Peter, can I make a comment? Can you hear me?
Yes.
Yeah, so actually with the FFDs, we found that 20 variables is enough. So I think, you know, the CST is fine, but in my comparisons, I didn't see a distinct advantage between the two.
Yeah, okay. Yeah, from what I've seen, they're all pretty close, like within, say, like, you know, plus or minus 2 variables to kind of get to like geometric tolerance, you know. One of the other motivations for using CSTs is that they're used in a lot of other aerospace software. So for example, like OpenVSP uses CST parameterizations as one of their freeform parameterizations. So you can kind of have a one-to-one mapping there without loss of fidelity if that's your downstream tool of choice.
Actually, what you mentioned is that you can have the same almost the same airfoil with very different parameters. That seems means it's ill-conditioned, right? I mean, the optimized, that's a flat spot in the design space.
Yes, this is
That'll cause
actually
problems.
so I was actually just talking with let me pull up a email from
Okay, guys. I think on a time check, we should not get down too far rabbit hole. So we have about 20 minutes, so I think we need to wrap up on the questions.
I'll talk to you about that. It's a good question. Yeah. Okay, cool.
Anyone else? All right, thank you very much.
So Peter, can you set up your, I don't know how you want to handle the discussion. Can we use your setup and,
Create breakout rooms and, yeah.
so can you set up a breakout room so,
Yeah.
so the committee can be there? Okay.
Hunter, you might want to make sure you turn the recording off.
Oh, yeah. Thank you.
I don't know if I'm actual about that. Yeah, no, I should turn it off.
Oh yeah, turn off the recordings. We are recording this.
I think for like a